All right, in part three, I will explain how we can plot poles. Poles are basically lines contained by the planes, and these are not just randomly oriented lines. These lines are at 90 degrees to the plane, so they are normal. Basically, a pole is a normal to the plane. So there will be 90-degree angle between this pole and strike orientation of the bearing plane. And if I hold this plane, this is the bedding plane in this case, and if I hold it horizontal, now you can see this pencil will be vertical because of that 90-degree angle between plane and its pole. And on projection, if you hold this plane horizontal, this plane will outline this primitive circle because of 0-degree dip angle, and this pencil will be a vertical line which will make a single point here in the center of projection. If I hold this plane vertical like that, this vertical plane will make a straight line in north-south direction and its pole will become horizontal. Because of that, it will make two half points along east-west direction, one here and one on the other end. In between, if layers are tilted at a dip angle, uh, like this for example, now look at the orientation of this plane and its pole. So this plane is now dipping this way, northeast direction, and dip angle of the bedding plane is angle between this plane and this horizontal surface. And its pole is making a point, a single point on the other side. So dip direction is northeast, bedding dip direction of bedding plane is northeast, and plunge direction of this pole is southwest. Because of the 90-degree angle between this pencil and plane, pole to this plane will appear in opposite quadrant. If bedding plane is dipping northeast, its pole will be in the opposite quadrant, which is southwest. And that will be 90-degree angle between this point and great circle representing this plane. So using this information, now let's plot some measurements and see how it will look like when we stare at it. So let's mark directions first. For each tracing paper, we should do that. And next we can plot a plane as a great circle, and now we'll find its pole. Just for this exercise, I will show both great circles and poles. Normally, we don't plot both great circle and pole. We just use either great circles or poles for planes. So let's make up a measurement. I'll make first. I will use an azimuth measurement. Let's make it 250. That's the strike orientation, and dip angle of 40 degrees. And we don't have to write dip direction because this is azimuth measurement recorded obeying right hand rule. We can use right hand rule and figure out dip direction. So it is 250 degrees. Here we are at 270, and if you come back 20 degrees, right here we are at 250 degrees strike orientation. And based on right hand rule, if you put your thumb parallel to 250 direction, open your hand, this layer is dipping northwest direction. So you can record it. So that's the dip direction. So we have a westward dipping plane. So great circle should be curved to northwest direction. So we already marked strike orientation on the primitive circle of the stairnet. Now we should rotate tracing paper and move this point to north-south reference line. Because south is closer, I will rotate tracing paper and move this point to south because we don't want to overturn that layer, right? And now we can count dip angle of the layer, which is 40 degrees northwest. So it's a westward dipping plane. We'll start from outer circle here at west and count 40 degrees from primitive circle towards center of the projection. So 10, 20, 30, 40. At this point, we have 40 degrees of dip angle. can draw that great circle and connect that circle to strike azimuth point on one side. And don't change position of paper because now we found the great circle, and now we will count 90 degrees from this great circle and find pole to display. Start from great circle and count 90 degrees in the opposite direction of dip. You will find a single point which will be pole to display. So here we have 40 degrees and start from here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Count 90 degrees. This is the point, I'll say P, pole to the bedding plane we used in this example. And this is one way you can start from great circle and count 90 degrees in the opposite direction of dip. The second way, so this distance here between great circle and pole, it is 90 degrees. The second way, maybe easier way, instead of starting from here and counting 90 degrees, we can start from center of the projection and count dip angle of the bedding plane in the opposite direction. It should take you to the same point. So if you start from here and count 40 degrees, 1, 2, 3, 4, you see you come to the same point. Because here we have dip angle of the bedding plane, right, which is 40 degrees. And at the center of projection, we have 90 degree dip angle. So between this point and great circle, what's left, it's 50 degrees. And from great circle to the pole, which is 90 degrees away from the plane, we also have 90 degrees, right? Because of that, what's left between center and pole, it is 40 degrees. So from here, 0 to great circle, 40 degrees, that's the angle of the plane. And from great circle to the pole, to the center of the projection, 50 degrees left because this distance is 90 degrees. Also, if you start from from great circle to the pole, we know there's 90 degree angle. So if you subtract 50 from 90, 40 degrees will be left between center and pole. So this is the logic behind it. You don't have to do this all the time, but basically you can start from great circle and count 90 degrees in the opposite direction of dip. That's one way. Or you can just start from center of the projection and count 40 degrees the dip angle of the measurement bedding plane in the opposite direction of dip. Let's go back to north and see what happened. Now we have a great circle which is curved to northwest direction and consistent with the direction of the measurement. And this is a great circle. And where is the pole of this plane, which is right here in southeast quadrant. So dip direction is to the northwest and pole will appear in southeast quadrant because of the 90-degree angle between this plane and line. So this is how you plot pole in azimuth if you have an azimuth measurement. Same with quadrant basically. And if you have a quadrant measurement, let's say let's make it this time north 40 east, not 40 west, and dip angle of 20 degrees to northeast. Okay. So first we find the strike along the perimeter circle. Start from north and count 40 degrees in the direction of west. 1, 2, 3, 4. That's the strike orientation of this plane, north 40 west. And north is closer. I will rotate tracing paper and move this point to north. And now I can use this east-west line or equator and count dip angle of 20 degrees. But the tip direction is east this time. So because of that, we'll start from this end, eastern end of the line and count 20 degrees from outer circle, 0, 10, 20. So here we have 20 degrees. So I will use a different color this time. So this is 20 degrees. So here we have 20 degrees. So I will use the second shorter way. Start from center and count 20 degrees in the opposite direction of dip because it's dipping this way. I'll count 20 degrees in opposite direction. 1, 2, and I'll mark this point. That's the pole to display. Let's try the first way. First method, count in 90 degrees. So here 20, 30, 40, 50, 60, 70, 10, 20, 30, 40, 50, 60, 70, 80, 90. So we are basically getting to the same point. So let's rotate tracing paper and check our solution. This red great circle is curved with northeast direction, which is the dip direction in recorded measurement, and pole to this plane appears in southwest quadrant, which is uh, opposite direction of northeast quadrant. So it looks like we did everything correctly. And also distance between this point and great circle, it's yeah reasonable. It's 90 degrees. If you find this pole point really close to great circle, just make sure and check your answer again because this is like the ideal distance between great circle and pole to that pole plane. So this is how we plot poles. Like I said, when we have extensive amount of measurements, working with points is very ideal and practical. Just imagine you don't have all these lines and everything, you just have a point. And that single point represents these measurements.